hurricane doubled its wind speed in 30 hours this weekend, 500 miles off the coast of California, where there is nobody for it to hurt. Genevieve went from 80 miles an hour to 160, Category 1 to Category 5, 4 rungs of the scale, in about a day and a quarter. It is the first Category 5 this ocean has produced since 2024. Tonight we walk the whole thing, hour by hour, what it did, where it is now, and why it will never touch land. Then we look at what built it, because Genevieve will be gone by the weekend, and the thing that made it is not going anywhere. That is the part almost nobody is talking about. What exactly is in that water? One thing before we get into it. If you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. Also, drop a comment and tell me where you're watching from tonight. Now, let's get into it. Part 1, 80 to 160. At 8 o'clock on Saturday evening Mountain Time, the strongest sustained winds inside Hurricane Genevieve were 80 miles an hour. That is a real hurricane. It is not a rumour of one. 80 miles an hour is a Category 1 on the Saffir-Simpson scale, the bottom rung of the ladder, and if you have ever stood outside in it, you know it is not something you argue with. 80 miles an hour peels shingles off a roof in long curling strips. It puts a carport through a fence. It snaps the shallow-rooted trees first, the ones people planted too close to the house, and it drops power lines across streets, and somewhere in your neighbourhood a transformer makes a sound like a gunshot and then everything goes dark. It is a serious storm. It is also, by the standards of what the ocean is capable of building, an unremarkable one. Storms like that form in the Eastern Pacific most years, several times a season, and most of them wander off into open water and die quietly without anyone outside the forecast offices learning their names. By 2 o'clock on Monday morning, 30 hours later, the strongest sustained winds inside Hurricane Genevieve were 160 miles an hour. I want you to sit with the gap between those two sentences for a second, because everything else in this video lives inside it. The storm did not strengthen. The storm did not intensify. Those words are too polite for what happened. The storm doubled. It took the raw number that describes how fast air was moving around its centre, and it multiplied that number by 2, and it did it in roughly the amount of time it takes most people to work a shift, sleep, work another shift, and sleep again. Category 5 begins at 157 miles an hour. There is nothing above it. The National Hurricane Centre's own damage description for that category does not describe damage in the way you might expect, with percentages and repair estimates. It describes the destruction of the frames of houses. It talks about total roof failure and wall collapse. It says that residential areas will be isolated by fallen trees and power poles, and that most of the area will be uninhabitable for weeks or months. That is the language. Uninhabitable. Weeks or months. So Genevieve did not climb one rung. It climbed 4. Category 1 to Category 2 to Category 3 to Category 4 to Category 5, without pausing on any of them long enough to be worth mentioning, and the entire ascent took about a day and a quarter. It is worth walking that ladder properly, because the rungs are not evenly spaced and most people assume they are. Category 1 runs from 74 to 95 miles an hour. Category 2 picks up at 96 and runs to 110. Category 3, and this is where a storm officially becomes a major hurricane, starts at 111 and runs to 129. Category 4 covers 130 to 156, and then Category 5 begins and does not end. The important thing about those brackets is that the damage does not scale the way the numbers do. Wind damage rises roughly with the square of the wind speed, and in some structural failure modes faster than that. A storm with twice the wind speed does not do twice the damage. It does something closer to 4 times, and in practice considerably worse than 4 times, because building materials have failure thresholds, and once you cross them, the structure does not degrade gracefully. It comes apart. Doubling from 80 to 160 is not a doubling of anything a person on the ground would experience. It is the difference between a storm that damages a town and a storm that removes one. Now, there is an official term for this, and the official term has an official number attached to it, which is helpful, because it lets us stop using adjectives and start using arithmetic. The National Hurricane Center defines rapid intensification as an increase in a storm's maximum sustained winds of at least 35 miles an hour, 30 knots, over a 24-hour period. That is the bar. Clear that bar and your storm has officially undergone rapid intensification. It goes in the record. It gets flagged. Forecasters talk about it in their discussions with a particular tone of voice, because rapid intensification is the thing that keeps them awake. 35 miles an hour in 24 hours. That is the threshold. Genevieve did approximately 80 miles an hour in about 30 hours. Run that against the bar and you get something well over double the qualifying rate, and it did not politely fit inside one 24-hour window and stop. It kept going. The intensification ran through more than a full day, and then some, and it did not taper off gently at the end. It simply arrived at the top of the scale because there was nowhere else for it to go. This is the first Category 5 hurricane the Eastern Pacific has produced since Hurricane Christy, back in October of 2024. It is also, and this is the detail that made me stop and read the line twice, the Northern Hemisphere's first major hurricane of the entire 2026 season. Think about what that actually means. A hurricane season does not usually work like this. Ordinarily you get a ramp. You get a tropical storm in June that never quite organises. You get a Category 1 in early July that scares the shipping lanes and dissipates. You get a Category 2, then a Category 3, and by the time the peak of the season arrives, the basin has been rehearsing for months. That is the normal shape of it. The atmosphere warms up to the idea. The Northern Hemisphere did not do that this year. Across every basin north of the equator, the first storm to reach major hurricane status, Category 3 or higher, did not stop at Category 3. It went straight to the top of the scale. The hemisphere's opening act was the ceiling, and I want to be specific about the geography of that claim, because it is broader than it sounds. The Northern Hemisphere's tropical cyclone basins include the Atlantic, the Eastern Pacific, the Central Pacific, the Western Pacific, which is by a wide margin the most productive basin on the planet, and the North Indian Ocean. All of them. Every one of those basins had been running for months, and the first storm in any of them to cross the major hurricane threshold of 111 miles an hour did not stop there, or 40 miles an hour later, or anywhere at all until it ran out of scale, and it happened in July. The Eastern Pacific has a season, and that season has a shape, and the shape peaks from late August into September. That is when the water has had the entire summer to absorb heat, when the sun has been working on it for months, when the accumulated warmth is at its deepest. That is the window. That is when this basin does its heaviest work. This is the final week of July. The basin has not gotten to the good part yet. So where is it? As of the 1500 hours Universal Time Advisory on Monday, Genevieve's center was several hundred miles south-southwest of the Baja California Peninsula, roughly 520 miles off, and it was moving northwest at about 13 miles an hour. Which brings us, immediately, to the part of this story that ought to be reassuring and somehow is not. It is not going to hit anything. That is not my read. That is the official position stated plainly. There are no direct impacts to land expected from Hurricane Genevieve. It is what forecasters call a fish storm, which is exactly as dismissive as it sounds. A hurricane whose entire violent, magnificent 4-category life happens over open water, where the only things in its path are fish, and the fish, I am told, are fine. So here is a fair question, and I want to answer it honestly rather than dodge it. Why are we here? Why spend the next 2 hours on a hurricane that will not injure a single person, damage a single building, or require a single evacuation order? There are days when this channel covers earthquakes that killed people, eruptions that closed airports, floods that took houses off their foundations. This storm will do none of that. It will spin northwest into cooler water over the next several days, its eye will fill in, its winds will fall away, and eventually the National Hurricane Center will issue a final advisory on a disorganized area of low pressure, and Genevieve will stop existing. We are here because the storm is not the story. I want to be careful with how I say this next part, because I am going to spend most of this video building to it, and I do not want to spoil it in the first 10 minutes, but you deserve to know the shape of where we are going. Hurricane Genevieve is a symptom. It is a reading. It is the number that came up on a gauge, and the gauge is attached to something much larger than one storm, something that will still be there long after this storm has a past tense. The thing that made Genevieve is not going anywhere when Genevieve goes away. Now, if you have watched this channel for any length of time, you know that our usual posture is the opposite of this. Normally we are the people pointing at the quiet reading. Normally the story is that the ground has gone still in a place where it should be noisy, or the tremor count is climbing while nothing visible happens on the surface, and the whole argument is that the silence is the thing you should be watching. The dramatic event is usually the distraction, and the quiet measurement underneath it is the warning. Tonight that is inverted, and I want you to hold on to the inversion, because it is the shape of the entire video. Tonight the dramatic event, a Category 5 hurricane, 160-mile-an-hour winds, the top of the scale, is the harmless part. It genuinely is. And the quiet measurement underneath it, a number published once a year in a journal that almost nobody outside a specific corner of oceanography ever reads, is the part that should bother you. We will get there. For now, sit with the arithmetic, because the arithmetic is the whole reason I opened a file on this storm at all. Something in that patch of ocean, 500 miles off the coast, was able to take an ordinary Category 1 hurricane and turn it into a Category 5 in 30 hours. Not gradually, not over the course of a week of favourable conditions, in a day and a quarter. And whatever was in that water to allow it is still in that water tonight, and it is in a great deal of other water besides. The question is not what Genevieve is going to do. Genevieve is going to die at sea. The question is what the ocean just told us it can do. Part 2. What rapid intensification actually requires. A hurricane is a heat engine. That is not a metaphor I am reaching for to make this sound more interesting than it is. It is a literal description of the machine. The engine takes in warm, wet air at the bottom close to the sea surface. That air rises because warm air does. As it rises, it cools, and as it cools, the water vapour inside it condenses into liquid droplets, and condensation releases heat. The same heat that went into evaporating that water off the ocean surface in the first place, now handed back to the atmosphere at altitude. That released heat warms the surrounding air, which makes it rise faster, which pulls more warm wet air in underneath, which rises and condenses and releases more heat. The system feeds itself. At the top 30 or 40,000 feet up, the exhausted air spreads outward and sinks, and the whole thing keeps turning as long as the fuel keeps coming. Everything else about a hurricane, the spiral bands, the eye wall, the storm surge, is plumbing built around that one exchange. Warm water in at the bottom, work out, exhaust at the top. Which means that if you want to understand why one storm stalls at Category 2 and another climbs to Category 5 in 30 hours, you have to look at the fuel and the plumbing, and there are 5 things that have to line up. The first is sea surface temperature, and this is the one everybody knows. There is a conventional floor for maintaining a tropical cyclone, and that floor sits at about 26.5 degrees Celsius, which is roughly 80 degrees Fahrenheit. Below that, the engine cannot keep itself running. The evaporation rate is too low, the air is not wet enough or warm enough, and the storm starves. Above it, the machine works. The further above it you go, the harder it works. The second thing is the one almost nobody talks about, and I want to introduce it now and then leave it alone for a while, because it turns out to be the load-bearing beam of this entire video. The second thing is how deep the warm water goes. Here is why that matters, and I want to walk through the mechanism carefully, because it is genuinely elegant and it is the reason most hurricanes never become monsters. A hurricane is enormous and it is violent, and it does not sit politely on top of the ocean. It churns it. The wind field drags the surface, and the surface drags the water below it, and the whole upper layer of the ocean under a hurricane gets stirred like a pot. That stirring pulls water up from below and mixes it into the surface layer. Now think about what that means. If the warm layer is thin, if you have a pleasant bath temperature skin sitting on top of cold water a few dozen meters down, then the storm's own churning drags that cold water up into the surface layer directly beneath itself. The sea surface temperature under the eye drops, the fuel gets colder, and the storm, entirely by its own hand, starves itself. Hurricanes do this constantly. It is one of the most common ways a promising storm fails. It intensifies, and the intensification produces stronger winds, and the stronger winds churn harder, and the harder churning brings up colder water, and the storm chokes on its own exhaust. The technical term for the cold patch it leaves behind is a cold wake, and you can see them from orbit. A scar of chilled water trailing behind a hurricane's track, sometimes for 1,000 miles. So the storms that do not cap themselves are the storms sitting over warmth that goes down a long way. If the warm layer is deep, the churning does not accomplish anything. The storm stirs the pot and brings up more warm water. The fuel does not run out, and that is when a hurricane gets to find out what it is actually capable of. I am going to leave that there for now. Remember it. The third ingredient is low vertical wind shear, and shear is worth explaining physically rather than as a piece of jargon. Wind shear means the wind is doing different things at different altitudes, blowing faster higher up or blowing from a different direction. Picture the hurricane as a chimney standing straight up out of the ocean. All that warm, wet air needs to go up through the chimney and out the top, and the whole system depends on the chimney being vertical, with the top stacked neatly over the bottom. Shear tilts the chimney. It shoves the upper part of the storm off to one side while the lower part stays put, and now the heat being released at altitude is not sitting over the low-level circulation that is producing it. The engine is venting sideways. The feedback loop breaks. Strong shear will tear a hurricane apart in a day, and weak shear will let it stand up straight and run. The fourth ingredient is mid-level humidity. Dry air is poison to a hurricane. If dry air gets entrained into the storm's core, it evaporates the cloud droplets, and evaporation cools the air, and cooled air sinks instead of rising, and sinking air in the middle of your updraft is the meteorological equivalent of pouring water into a carburetor. A moist column, top to bottom, lets the convective towers keep building without interference. The fifth ingredient is an inner core that is already organized. This is the one that gets forgotten, and it matters enormously. Rapid intensification is not how a storm gets started. It is what an already competent storm does when the last constraint comes off. You need a closed circulation, a defined center, an eye wall that has begun to form. The storm has to already be a machine before it can be a fast machine, and here is the difficulty. The thing that makes this genuinely hard rather than merely complicated. Any one of those 5 missing, and rapid intensification does not happen. Warm water but high shear, nothing. Low shear but dry air, nothing. Everything perfect but a sloppy disorganized center, nothing. The ingredients do not add. They multiply, and any one of them at 0 takes the whole product to 0. But get all 5 aligned at once, and the storm stops being limited by its environment and starts being limited only by physics. It runs toward its thermodynamic ceiling, the theoretical maximum intensity that patch of ocean and that column of air can support, and it runs there fast. This, incidentally, is why hurricane forecasting has a split personality that most people never notice. Track forecasting, where the storm is going, has improved enormously over the past several decades. The 5-day track forecast today is roughly as accurate as the 3-day forecast was a generation ago. It is one of the genuine triumphs of operational meteorology, and it has saved an enormous number of lives. Intensity forecasting, how strong the storm will be, has improved far more slowly. And within intensity forecasting, rapid intensification is the specific failure mode. It is the thing the models miss. I am going to come back to that, and when I do, it is going to stop being an interesting technical footnote and start being the most important thing in this video. So what about Genevieve? What did the ocean under this particular storm look like? The water beneath and ahead of Genevieve's track has been reported in the range of 86 to 94 degrees Fahrenheit. Let me convert that, because the Fahrenheit numbers sound like a warm bath and the Celsius numbers sound like what they actually are. 86 degrees Fahrenheit is 30 degrees Celsius. 94 degrees Fahrenheit is a little over 34 degrees Celsius, and the floor, the temperature below which a tropical cyclone cannot sustain itself, is 26.5. So the water under this hurricane was running somewhere between 3.5 and nearly 8 degrees Celsius, above the minimum required to keep a hurricane alive at all. Not above average, above the survival threshold. The margin was not thin. The margin was enormous. That explains a great deal. It does not explain everything, and I want to be precise about the gap because the gap is where this video is going. Sea surface temperature is a skin reading. It is the temperature of the top layer, the part a satellite can see, the part a thermometer on a buoy touches. It tells you what the surface is doing. It does not tell you what is underneath the surface, and as we just established, what is underneath the surface is the difference between a storm that chokes itself in 12 hours and a storm that climbs 4 categories in 30. Genevieve did not choke itself. A storm that size, that intense, mixing the ocean that hard, should have been fighting its own cold wake by the end of the first day. It did not fight anything. It just kept climbing. The 5 ingredients tell us how a hurricane intensifies rapidly. They do not tell us why the ocean happened to have all 5 of them stacked up and ready in the last week of July, in a basin that has not even reached its peak season yet. That answer is not in the sky. Part 3. Where the storm stands right now. 1500 hours, Universal Time, Monday the 27th of July 2026. At that moment, the center of Hurricane Genevieve was located near 16 degrees north latitude, 113 degrees west longitude. That is open Pacific, well south and west of the tip of the Baja California Peninsula, with nothing around it in any direction but water. Maximum sustained winds at that fix were 135 knots. In the units most people think in, that is about 155 miles an hour. Gusts were running to 165 knots, and the minimum central pressure was 929 millibars. That last number is the one I want to spend a moment on, because pressure is the measurement that tells you what is really going on inside a storm, and most people have no reference for it at all. Atmospheric pressure is the weight of the air above you. All of it. The entire column of atmosphere stretching from the top of your head to the edge of space, pressing down. At sea level, on an ordinary day, in ordinary weather, that column weighs in at around 1,013 millibars. That is the baseline. That is the number the atmosphere sits at when nothing interesting is happening. Inside the eye of Hurricane Genevieve, that column weighed 929. 84 millibars of the atmosphere had in effect been removed. Not pushed aside, evacuated upward and outward by the engine, thrown out the top of the chimney and flung away at altitude. The storm had excavated a hole in the atmosphere above itself, and air, being air, wants to fill that hole. The steeper the drop from the surrounding pressure to the pressure at the center, the harder the atmosphere rushes inward to equalize it. That rushing is the wind. That is all wind ever is. Air moving from higher pressure to lower pressure. So when you hear that a storm has a central pressure of 929 millibars, what you're being told is the size of the hole, and the size of the hole is what sets the speed of everything falling into it. 929 is a deep hole. It is not a record. We will get to the record later, and the record is genuinely shocking. But it is the kind of number that belongs to a serious, mature, fully developed hurricane, running near the upper end of what its environment allows. Now, you will have noticed that 155 miles an hour is not 160. Genevieve had eased slightly off its Category 5 peak by the time of that afternoon fix, back down into high-end Category 4 territory. That is completely normal, and it is worth explaining why, because a storm weakening slightly is not a storm ending. Intense hurricanes oscillate. They breathe. The most common reason is a process called an eye wall replacement cycle, and it happens to nearly every hurricane that reaches this kind of intensity. The eye wall, the ring of towering thunderstorms immediately around the eye, where the strongest winds live, contracts as the storm intensifies, getting tighter and faster, the way a spinning skater pulls their arms in. But a very tight eye wall is unstable. Eventually a second ring of convection organizes further out, and that outer ring begins to choke off the inflow feeding the inner one. The inner eye wall starves and collapses. The outer ring takes over and contracts in its turn. While that handoff is happening, the storm's peak winds drop, sometimes by 15 or 20 miles an hour. Its wind field also gets broader, and then, if conditions are still favorable, the new eye wall tightens up and the storm re-intensifies, sometimes to a higher peak than before. Shear fluctuations do the same thing on shorter timescales, and so does the water temperature along the track. A storm crossing a patch of slightly cooler water will ease off and then recover on the other side. None of this means the storm is finished. It means the storm is alive and the machine is running through its normal cycles. For contrast, look at where Genevieve was 12 hours earlier. At 00 hours Universal Time, it was roughly 700 miles southwest of the Mexican coast, with winds of 130 to 135 knots. So across that half day it stayed essentially pinned at the same extraordinary intensity, moving northwest, holding its structure together. There is also an independent reading worth mentioning, because it is the kind of thing that generates confusion, and I would rather diffuse it now. NASA's Earth Observatory Event Tracking System logged Hurricane Genevieve at 140 knots as of its 600 hours Universal Time update. The National Hurricane Center's fix 9 hours later put it at 135. Those are not contradictory. They are different products, generated by different systems, at different times, sampling a storm that is actively changing. 140 knots at 6 in the morning and 135 knots at 3 in the afternoon is a storm easing slightly across 9 hours, which is exactly what an eye wall replacement looks like from the outside. When you see two agencies quoting different numbers for the same hurricane, the usual explanation is not that someone is wrong. It is that they are two instruments looking at a moving target at two different moments. Put all of it together, and you can reconstruct the physical object without ever seeing a satellite image. A compact, deeply pressured core, a well-defined eye, an eye wall producing sustained winds of 155 miles an hour, with gusts running about 22% higher than the sustained figure, which is a healthy ratio and tells you the convection is vigorous rather than decaying. A storm at the top of its game, and it is heading northwest at about 13 miles an hour, which is a walking pace for a hurricane, into progressively cooler water and an increasingly hostile shear environment. Which means the forecast, in plain terms, is decay. Genevieve is going to run out of fuel. Sometime in the next several days it will weaken below hurricane strength, and then below tropical storm strength, and the final advisory will be written on a remnant low, and that will be that. Before we go any further into what this storm means, I want to plant a flag on the honest baseline, because it would be very easy to make this sound more unprecedented than it is, and I do not want to do that. In reliable records going back to the early 1970s, 14 hurricanes have reached Category 5 intensity in the Eastern Pacific Basin, defined as the region east of 140 degrees west longitude. 14. Genevieve is the 15th. 3 of them came in 2018 alone, Lane, Wallaca and Willa all in the same season. 2 came in 2023, and one of those 2 is going to matter enormously later in this video. 1 came in 2024, and that was Christy, which reached Category 5 on an October afternoon while sitting almost 1,000 miles southwest of Los Cabos, and, like Genevieve, never touched anything. That definition, east of 140 degrees west, is worth pausing on, because basin boundaries are administrative lines rather than physical ones. 140 west is roughly the longitude at which responsibility for forecasting hands over from the National Hurricane Center in Miami to the Central Pacific Hurricane Center in Honolulu. A storm does not notice the line. It crosses it, gets a new forecast office, and keeps doing whatever it was doing. Which means the count of 14 is a count of storms that reach the top of the scale, while inside a particular administrative box, not a count of everything the wider Pacific has produced. The real number of Category 5 hurricanes this ocean has generated is considerably larger. We are looking at one slice of one ocean. So let me say this as plainly as I can, because the honesty matters more to me than the drama. Category 5 hurricanes happen in this basin. They are not common, but they are not extraordinary either. A Category 5 forming in the Eastern Pacific is not, by itself, evidence of anything. The anomaly is not the category. The anomaly is the 30 hours. That is the number that does not sit comfortably alongside the other 14. That is the number that made me open this file. A storm reaching the top of the scale is a thing this ocean does from time to time. A storm reaching the top of the scale from a standing start in a day and a quarter in July before the season has properly begun is a different kind of statement. And every single measurement we have just walked through, the pressure, the wind, the gust ratio, the structure, the fact that it did not stall is not really a measurement of Hurricane Genevieve at all. Each one is a reading taken off the water underneath it. The storm is the needle, the ocean is the dial, so the storm is an instrument, and the reading it just took in the last week of July, 500 miles from the nearest coastline, is the part almost nobody is talking about. Part 4. Why it will never touch land, and why that isn't comfort. There is a phrase forecasters use for a hurricane like this one, and it is almost affectionate. They call it a fish storm. A fish storm is a tropical cyclone whose entire life, formation, intensification, peak, decay, dissolution, takes place over open ocean. It never touches a coastline. It never generates a warning. It never appears on the evening news in any country. It is born at sea, it does something magnificent and violent at sea, and it dies at sea, and the only witnesses are satellites and the occasional very unlucky cargo ship that got its routing wrong. Genevieve is going to be a fish storm. The mechanics of that are mostly about steering. Hurricanes do not choose where they go. They are carried, like a cork in a river, by the larger flow of the atmosphere around them, primarily by the position and strength of the subtropical ridge, a semi-permanent area of high pressure that sits over the ocean and steers everything on its southern flank. Genevieve's northwest heading is the ridge's decision, not the storm's, and that heading takes it away from Mexico rather than toward it. And out there to the northwest, waiting is the thing that will kill it. Cooler water, because the further north you go, the less direct sunlight the ocean receives and the less heat it stores. Stronger shear, because you are approaching the mid-latitude westerlies where the upper-level winds pick up speed. The storm is walking at 13 miles an hour toward its own execution, This is the general climatological pattern of the Eastern Pacific, and it is the reason this basin produces so many hurricanes that nobody outside of meteorology has ever heard of. The steering flow tends to carry systems west and northwest, out into a progressively cooling ocean away from the Mexican coast. The basin is enormously productive and mostly harmless, which is a strange combination and a very lucky one for everyone living along that coastline. So here is where I want to turn this around, because the obvious reading of everything I just said is that Genevieve does not matter, and I think the obvious reading is exactly backward. A fish storm is the cleanest natural experiment you can get. Think about what a landfalling hurricane does to your data. The moment a storm approaches a coastline, everything gets contaminated. Friction from the land surface starts dragging on the circulation. Terrain, mountains in Mexico's case and substantial ones, disrupts the inflow and tears at the structure. Shallow coastal water behaves differently from deep ocean. Dry continental air gets pulled into the circulation from inland. By the time a hurricane makes landfall, its intensity is a mixture of what the ocean gave it and what the land started taking away, and separating those two things is genuinely difficult. Genevieve has none of that. No land interaction, no friction, no terrain, no entrained continental air. Just a storm and the water it is sitting on, isolated with every other variable held at zero. Which means the intensity it reached is, as closely as we can practically measure such a thing, what that patch of ocean could support, not what it could support minus terrain effects, minus friction, minus dry air. What it could support, full stop. The storm is a probe. Somebody dropped a measuring instrument into the Eastern Pacific in the last week of July, and the instrument returned a number, and the number is 160 miles an hour in 30 hours. And now I need to tell you what that number actually implies, because this is the point where the surface temperature stops being a sufficient explanation. Go back to the churning. A hurricane the size and intensity of Genevieve mixes the upper ocean hard. We're talking about a system dragging on the sea surface with hurricane-force winds across a footprint hundreds of miles wide for days. That mixing reaches down. It pulls water up from below and blends it into the surface layer. If the warm layer beneath Genevieve had been thin, if that 86 to 94 degree water had been a skin, a shallow lens of warmth sitting on top of something cooler, then the storm would have upwelled that cooler water into its own circulation. Its own fuel would have chilled. The intensification would have stalled somewhere around Category 2 or Category 3, and it would have left a cold wake behind it and wandered off, and I would be talking about something else tonight. That did not happen. Genevieve did not stall. It did not fight its own cold wake, because it did not produce a meaningful one. It went from 80 to 160 without the ocean ever pushing back. There is only one way that is possible. The warmth goes deep, and that quantity, how much heat is stored in the water column, not what temperature the top of it happens to be, has a name, and it is the name I have been circling for the last hour. It is called ocean heat content. Sea surface temperature is a skin reading. It is what a satellite sees, what a buoy touches, what a thermometer at the surface reports. It is genuinely useful, and it is genuinely incomplete, in the same way that knowing the temperature of the top inch of a swimming pool tells you very little about how long you could stay in it. Ocean heat content is the other question. It asks how much energy is actually stored in the column, down through the mixed layer, down through the thermocline, down to 2,000 meters. It is a measure of the size of the reservoir rather than the temperature of the lid. And that distinction, surface warmth versus stored warmth, is the entire difference between a hurricane that caps itself at Category 2 and one that reaches the top of the scale in a day and a quarter. It is the difference between a storm that starves and a storm that does not. Every other ingredient can be perfect, and if the warm layer is thin, the storm will kill itself with its own strength. So, how do we know what the ocean heat content is? This is not a thing you can see from orbit, because the satellite cannot look through water. We know it two ways, and both of them are quietly extraordinary. The first is a global network of autonomous profiling floats. These are cylindrical instruments, a couple of meters long, scattered across every ocean basin on Earth in the thousands. Each one follows a cycle. It sinks to a depth of around 2,000 meters, drifts with the current for several days, then adjusts its buoyancy and rises slowly back to the surface, taking temperature and salinity measurements the whole way up. When it surfaces, it transmits its profile by satellite, then sinks and does it again. Each float does this for years. Nobody drives them. Nobody retrieves them. They just drift and dive and report over and over and between them they take a continuous temperature profile of the upper half of the world ocean. The second method is satellite altimetry, and the physics of it is beautiful. Water expands when it warms. A column of ocean that is storing more heat is physically taller than the same column storing less. Not by much, but by an amount that a radar altimeter in orbit can measure with startling precision. So a satellite measuring the height of the sea surface is, indirectly, measuring how much heat is in the water beneath it. Put those two systems together, thousands of floats profiling from within, satellites measuring expansion from above, and you get a number, a single global figure for how much heat is stored in the top 2,000 meters of the world ocean, updated every year. That number is published annually. It appears in a peer-reviewed journal. It is not hidden, it is not controversial among the people who work on it, and it gets almost no attention at all outside a fairly small professional community. That number is what this video is actually about, and I am not going to give it to you yet because I want you to arrive at it the way I did, after understanding exactly what it governs. So hold the question. For now, come back to the fish storm and to the thing that makes it worth 2 hours of your evening. The fact that Genevieve is going nowhere, that it will harm no one, that it will not so much as blow a roof tile off a single building. That is not a reason to look away. That is what makes it readable. There is nothing confounding the measurement. No coastline, no mountains, no friction, no ambiguity. A storm and the water, and a number that came back clean. The storm is the instrument. The ocean is the reading, and we are about to look at the reading. Which leaves one question standing over the rest of this video, and I want you holding it as we go. If the water off the coast of Mexico was deep enough and warm enough in July to let an ordinary hurricane double its wind speed in 30 hours over open ocean, where it could not touch anyone, what happens the next time that same water is sitting somewhere a storm can actually reach people? Part 5. The beaches already feeling it. A hurricane at the top of the scale, 600 miles of open water in every direction, and not one person in its path. That is where we left it. Now let me show you the one place Genevieve is touching, and it is not where you would expect. On Monday morning, along the southwestern coast of Mexico and the southern reaches of the Baja California Peninsula, the water started behaving strangely. Large swells were already arriving, life-threatening surf, dangerous rip currents, and the forecast was for that hazard to spread northward through the day, up the peninsula, into places where the sky was completely clear and the wind was doing nothing at all. This is one of my favourite pieces of physics in all of meteorology, and it is also one of the most quietly lethal, so let me walk you through how it works. When a hurricane's wind field blows across the sea surface, it does two things. It drags the water along, which creates current, and it pushes on the water, which creates waves. The waves generated directly under a storm are chaotic, a confused, steep, ugly sea with waves of every size running in every direction at once. If you were unfortunate enough to be in it, it would not look like waves at all. It would look like the ocean had come apart. But those waves do not stay under the storm. They radiate outward in every direction, at speeds that depend on their wavelength. And here is the crucial part. Longer waves travel faster than shorter ones. So as the wave field spreads outward from the storm, it sorts itself. The long, fast waves outrun the short, slow ones, and by the time the energy has travelled several hundred miles, what was a chaotic mess has organised itself into clean, evenly spaced, long-period swell. Those swells travel much faster than the storm that made them. A hurricane moving at 13 miles an hour is being outrun by its own waves, which can cover several hundred miles in a day, which means the energy arrives at a coastline first, sometimes days before the storm would, and in Genevieve's case, days before a storm that is never going to arrive at all. So picture what that looks like on a beach in southern Baja on a Monday morning in July. The sky is clear, the sun is out, the air is still or close to it. Every visual cue a human being uses to assess whether the ocean is safe is telling you that the ocean is safe. And then a set arrives that was generated by 160-mile-an-hour winds 600 miles away. The mismatch between what the sky is saying and what the water is doing is the entire hazard. People drown in exactly this scenario, on exactly these days, and they drown because nothing about the morning looked wrong. Nobody stays out of the water on a beautiful day. There is no siren for this. There is no visible wall of weather on the horizon to prompt second thoughts. There is just a long, low, heavy set of waves arriving out of a clear sky, carrying energy from an engine running over the horizon. The rip current mechanism follows directly from it, and it is worth understanding because it is the specific thing that kills people. When wave sets break on shore repeatedly, they push water up the beach faster than it can drain back out evenly. That water piles up. It has to return seaward somehow, and it does not return the way it came, spread out across the whole beach face. It finds the path of least resistance, a gap in a sandbar, a channel, a low spot in the bottom contour, and all that piled water funnels into that narrow gap and rushes offshore in a fast concentrated jet. The jet can run faster than an Olympic swimmer. It does not pull people under. That is the myth. It pulls them out straight offshore at a speed they cannot swim against, and the instinct of nearly every person caught in one is to swim directly back toward the beach, which means swimming directly into the current, which means exhausting yourself in open water a few hundred yards from a shoreline you can see perfectly clearly. The bigger and longer period the incoming swell, the more water gets piled on shore and the more violent the return flow, which is why a distant hurricane, a storm that produces no wind, no rain, and no cloud cover at the beach, is one of the most reliable producers of drowning conditions there is. The word period is doing quiet work in that sentence, and it is worth unpacking because it is the difference between ordinary surf and the kind that arrives from a Category 5. Wave period is simply the time between one crest passing a fixed point and the next. Locally generated wind waves on a breezy afternoon might have a period of 5 or 6 seconds. Swell radiating out from a major hurricane can arrive with periods of 15, 18, 20 seconds. That distinction is not cosmetic. The energy a wave carries and the depth of water it can feel both scale with its period. A long-period swell reaches down and interacts with the sea bottom much further offshore than a short-period wind wave does, which means it starts steepening earlier, breaks harder, and delivers vastly more energy onto the beach face per wave. Two swells of identical height but different period are completely different animals. One is a pleasant afternoon, the other rearranges the sandbar, so the sets arriving in southern Baja are not simply larger, they are longer, heavier, and spaced further apart, which introduces its own trap. Long-period swell tends to arrive in groups, with genuinely calm intervals between them. A swimmer wades out during a lull, sees flat water, decides the warnings were overcautious, and is 100 meters from shore when the next set arrives. Now, I want to be honest about proportion here, because it would be very easy to inflate this, and I am not going to. This is a minor hazard, genuinely minor compared to what a hurricane can do. Nobody is being evacuated. There is no landfall watch, no hurricane warning, no wind threat to any city, no storm surge inundating anything. The vast majority of people along that coast will experience Hurricane Genevieve as a slightly rougher than usual day at the beach, and nothing more. The National Hurricane Center's messaging is accurate and it is not hedged. No direct impacts to land are expected. I am spending time on the swell not because it is dangerous enough to build a video around, but because of what it demonstrates. The only part of this storm that reaches a human being at all is a wave that travelled 600 miles to get there, and that is the entire margin. That is what separates this outcome from a completely different one. Move the same storm 400 miles east and it is not a swell advisory. It is a Category 5 hurricane approaching the Mexican coast with an eye wall running 160-mile-an-hour winds. Same storm, same physics, same ocean underneath it, different longitude. The distinction between a scientific curiosity and a catastrophe in this case is geography, and geography is luck. It is where the subtropical ridge happened to be sitting this week, and which way the steering flow happened to be pointed, and it will be different next time and different again the time after that. Nobody controls it, and nobody can count on it. The water is not luck. The water is a condition. It was there before this storm formed, and it will be there after this storm dissipates, and it is not confined to the patch of ocean Genevieve happened to be sitting on. Which brings us to the number I have been holding back. Because the reason that water was capable of doing this, in July, before the season has properly started 500 miles from anywhere, is a measurement that has been climbing for 9 years without a single interruption. Part 6. The Reservoir. Underneath. In 2025, the heat stored in the top 2,000 meters of the world ocean reached the highest level ever recorded. That is not the remarkable part. Here is the remarkable part. It was the 9th consecutive year it had done so. The finding was led by Li Jingcheng of the Institute of Atmospheric Physics at the Chinese Academy of Sciences and published in the journal Advances in Atmospheric Sciences. And before we go anywhere near the number itself, I want to establish who produced it, because this is a video about trusting a measurement, and you should know where the measurement came from. 55 scientists, 31 research institutes, 10 separate research teams, spread across multiple countries, China, the United States, France, Italy, not one lab, not one nation, not one funding body, 55 people across 3 continents, working from a shared observational network, arriving at a shared number. The number is this. Between 2024 and 2025, the top 2,000 meters of the world ocean absorbed an additional 23 zettajoules of energy, with an uncertainty of about 8. Now, a zettajoule. I am going to assume, with no disrespect intended, that you do not have an intuition for a zettajoule, because almost nobody does, including a lot of people who work adjacent to this field. So let us build one from the bottom. A joule is a small unit of energy. If you lift a small apple 1 meter off a table, you have done roughly 1 joule of work. That is the scale. 1 apple, 1 meter. A kilojoule is 1,000 of those. A megajoule is 1,000,000. A gigajoule is 1,000,000,000. A terajoule is 1,000,000,000,000. And you keep going, petajoule, exajoule, and then, 4 steps past 1,000,000,000,000, you arrive at a zettajoule. A zettajoule is a 1 followed by 21 zeros worth of joules. The ocean took in 23 of them in a single year, over and above what it took in the year before. If that still does not land, and I would not blame you, the researchers offered 2 comparisons that do. The first is that the single-year increase in 2025 is roughly 39 times the total energy produced by all human activity on Earth in 2023. Every power station, every engine, every furnace, every turbine, every reactor, every barrel of oil burned in every vehicle in every country on the planet for a full year. Multiply the entire output of human civilization by 39, and you have the amount by which the ocean's heat content increased in 1 year relative to the year before. The second comparison is the one that stayed with me. 23 zettajoules delivered over a year works out to the energy of approximately 12 Hiroshima-scale bombs going into the ocean every second. Every second. Not 12 bombs, not 12 bombs a day. 12 per second, continuously, for a year, and then the next year the number is higher again. I want to slow down on the word continuously, because it is doing enormous work in that sentence, and it is easy to read past. An explosion is an event. It happens, and then it is over, and afterward you assess the damage and begin recovering. What is being described here is not an event. It is a rate. It is the steady-state condition of the planet's energy budget. It was happening while you watched the first hour of this video. It is happening now. It will be happening tomorrow, and the arithmetic does not care whether anyone is paying attention, and the ocean absorbs it quietly. That is the thing about water. It does not glow, it does not roar, it does not do anything at all that a person standing on a beach would notice. It just gets very slightly warmer, and it holds on. There is also a reason the measurement stops at 2,000 meters, and it is not arbitrary. 2,000 meters is roughly the depth to which the global float network reliably profiles, and it captures the layers where the overwhelming majority of the recent heat uptake has occurred, the mixed layer, the thermocline beneath it, and the intermediate water below that. Heat is going into the deeper ocean as well, below 2,000 meters, and that heat is also being measured, more sparsely and with greater uncertainty. So the 23 zettajoule figure is not the whole story. It is the well-observed part of the story, and the unobserved remainder does not run in the other direction. The measurement history matters too, because a 70-year record is not 70 years of equal quality. Before roughly the year 2000, ocean temperature profiles came overwhelmingly from ships, bottles lowered on cables, and later expendable probes dropped over the side and trailing a thin wire as they sank. That gave good coverage along shipping lanes in the Northern Hemisphere and almost nothing in the Southern Ocean, which is a very large fraction of the planet's water. The early record had to be reconstructed with statistical infilling, and it carried real uncertainty. The float network changed that. From the early 2000s onward, the ocean has been sampled by a distributed, autonomous, globally spread array that does not care whether a region is commercially interesting. The modern part of the record is dramatically better observed than the early part, which is worth knowing, because it means the recent record years are the ones we can be most confident about, not the least. Some context on where that number sits historically. It is the highest reading of any year since modern record-keeping began in the early 1950s. 70-odd years of measurement, and the top of the list is last year. And it is the 9th in a row, which is the detail that turns this from a data point into a trajectory. This is not a spike. A spike would be a single year that jumped and then settled back. 9 consecutive records is not a spike. It is a slope. As for what is driving it, the study names 2 things. The first is increased greenhouse gas concentrations, which is the answer you expected and which I am not going to belabor. The second is more interesting and less discussed. Recent reductions in sulfate aerosols. Here is what that means, and it is genuinely uncomfortable. For decades, industrial activity, particularly coal burning and heavy shipping fuel, pumped sulfur compounds into the atmosphere. Those compounds form tiny reflective particles that scatter sunlight back to space and seed brighter, more reflective clouds. They also cause acid rain and respiratory disease, which is why, over the past several decades and with real urgency in the shipping sector recently, the world has been cleaning them up. Cleaning them up was the right thing to do. It was unambiguously good for human health and for ecosystems. It also removed a reflective haze that had been masking a portion of the warming already in the system. We took off a pair of very dirty sunglasses, and the light was brighter than we remembered. That is not an argument for putting the sunglasses back on. It is an illustration of how much heat was already in the pipeline, waiting behind a screen we had built by accident. And now connect that back to what we established earlier, because this is the moment the 2 halves of the video lock together. Ocean heat content is precisely the quantity that determines whether a hurricane caps itself or does not. It is the depth of the warm layer. It is the size of the fuel tank rather than the temperature of the fuel cap. A storm sitting over a deep reservoir can churn as hard as it likes, and never reach anything cold enough to slow it down. Genevieve's 30 hours was a withdrawal from that account, and the account has been setting a record every single year for 9 years running. Part 7. The 9th year in a row. 9. That is the number I keep coming back to, more than the 23 zettajoules, more than the temperature readings, more than anything else in this story. Not because it is dramatic, it is the least dramatic number in the entire video, but because of what consecutive records mean statistically. A single record year is not evidence of much on its own. Climate systems are noisy. They have internal variability that operates on timescales of years and decades, and any given year can land high for reasons that have nothing to do with a long-term trend. If someone tells you a record was set last year, the honest scientific response is a shrug and a request for more data. 2 records in a row is mildly interesting. 3 starts to be difficult to attribute to chance. 9 in a row is not variability. 9 in a row is a forced trend. Something is pushing in one direction, consistently, without pause, and the noise is riding on top of it rather than producing it. So where is all this heat going, and why the ocean specifically? The answer is that the ocean is where the heat has always gone. When the planet's energy budget is out of balance, when more energy is arriving from the sun than is leaving to space, that surplus has to be stored somewhere, and the overwhelming majority of it, by a very wide margin, ends up in the water. The reason is a matter of physics and of sheer bulk. The atmosphere is thin and it is light. If you compressed the entire atmosphere to the density of water, it would be a layer about 10 meters deep across the whole planet. That is the entire sky. 10 meters. The ocean averages nearly 4,000 meters deep and covers more than 70% of the surface, and water has an enormous heat capacity. It takes a great deal of energy to change water's temperature compared with almost any other common substance. Air is easy to heat. Water fights you. Put those together and you get the situation we are in. The ocean can absorb staggering quantities of energy while its temperature moves only a little. This is why the surface temperature numbers always sound so modest. Fractions of a degree here or there, while the energy numbers are almost unreadably large. Both are true simultaneously. A small temperature change across an enormous mass of water is an enormous quantity of energy. And that is also the trap because it makes the problem easy to dismiss. A degree does not sound like anything. A degree is the difference between 2 rooms in the same house. But that degree, spread across a volume of water measured in hundreds of millions of cubic kilometers, represents an energy reservoir that has to go somewhere and do something. Then there is the inertia, which I think is the part people underestimate most. Heat that has gone into the ocean does not come back out on any timescale that matters to a human being. The deep ocean overturns on a schedule measured in centuries. Energy delivered to the water column this decade is committed. Even in a scenario where emissions stopped entirely tomorrow morning, the heat already in the ocean would continue expressing itself, through thermal expansion and sea level, through ice shelf melting from below, and through the specific thing this video is about, which is the fuel available to tropical cyclones. For a very long time, this is not a weather condition. Weather conditions pass. This is a state. And I think that is exactly why almost nobody talks about it. Air temperature is a headline. It arrives as a hottest day ever, a hottest month ever, a number a person can feel on their skin walking to a car, and it comes with photographs of thermometers and empty reservoirs. It is legible. It is also, in a strict physical sense, the smaller half of the story. The thin, light, fast-responding part of the system that reacts quickly and then reacts quickly the other way when conditions change. Ocean heat content arrives once a year, in a specialist journal, as a figure with a unit most people have never encountered, describing something happening a kilometre beneath a surface nobody can see. It generates almost no coverage. It is not photogenic. There is no footage of it. It is also the number that does not go back down, which means the quantity we pay the least attention to is the one carrying the largest share of the signal and virtually all of the commitment. That is not a conspiracy. Nobody suppressed it. It is simply a measurement that is boring to look at and impossible to argue with, and those two properties together are apparently enough to keep something out of public view indefinitely. Hurricanes are not the only thing that stored heat expresses itself through, and it is worth naming the others briefly, because they are the reason oceanographers care about this number in the first place. The most direct consequence is sea level. Water expands as it warms. The same physics that makes satellite altimetry work as a measurement technique also makes it a problem. A substantial share of observed sea level rise is not melting ice at all. It is thermal expansion, the same water occupying more space because it is warmer. Every zettajoule that goes into the column raises the sea a little, everywhere, permanently on human timescales. The second is what that heat does at the boundaries. Warm water reaching the underside of a floating ice shelf melts it from below, which is the mechanism that has driven the most alarming glaciological findings of the past decade, and it is a mechanism that has nothing to do with air temperature. The third is marine heat waves, prolonged regional stretches of anomalously warm water that have become dramatically more frequent and which bleach coral, displace fisheries, and reorganize entire ecosystems on a scale of months. All of those are downstream of the same reservoir. The hurricane story is one expression among several, and it happens to be the one with a Category 5 sitting in it this week. There is one more measurement worth putting alongside it. As of June of 2026, global sea surface temperature anomalies had climbed to record high levels for the period, and that finding came from two independent datasets, both showing the same thing. Two independent datasets matters more than it might sound. Different satellite instruments, different buoy and ship networks, different processing chains built by different institutions in different countries, with different assumptions baked into how they handle gaps and corrections and calibration drift. When two systems built separately arrive at the same answer, the probability that the answer is a processing artifact drops sharply. So bring this back to hurricanes, and be careful about the claim, because this is where these conversations usually go wrong. More stored heat, in a deeper layer, across a wider area means more places and more days on which all 5 of those rapid intensification ingredients can align at once. That is the actual mechanism. It does not mean every storm will intensify rapidly. It does not mean this specific hurricane happened because of it. Most storms will still be torn apart by shear or choked by dry air, or simply never organize in the first place, because the other 4 ingredients are still independent and still frequently unfavourable. What changes is the odds and the ceiling. More of the ocean, more of the time, is now capable of supporting a storm that runs to the top of the scale, if the other conditions happen to cooperate, which is why a storm nobody will remember, over water nobody lives near, is worth 2 hours of your time. Genevieve is not important. Genevieve is legible. It is a clean reading of exactly this quantity, taken in a place where no coastline, no terrain, and no friction got in the way of the measurement, and the reading came back at 160 miles an hour in 30 hours. Part 8. The El Niño building behind it. Minus 0.54, minus 0.37, minus 0.14, plus 0.13, plus 0.51, plus 0.98. Those 6 numbers are the last 6 seasons of the Oceanic Niño Index, and I read them out like that deliberately, because the shape of the thing is easier to hear than to read. The Oceanic Niño Index is a straightforward measurement with an outsized influence. It is a 3-month running average of the sea surface temperature anomaly, the departure from normal, in a specific rectangle of the central equatorial Pacific, a region designated Niño 3.4. When that average runs sufficiently above normal for long enough, the condition is called El Niño, sufficiently below La Niña. It is one number in one box of ocean, and it reorganizes weather on every continent. Walk the sequence. In November, December and January of 2025, the index sat at minus 0.54, cool side, La Niña adjacent. December through February brought it to minus 0.37, January through March, minus 0.14, approaching neutral. February through April crossed the line into positive territory at plus 0.13. March through May climbed to plus 0.51, and April, May and June of 2026 came in at plus 0.98. Status, El Niño. Trend, warming. That is a swing of plus 1.52 across 6 overlapping seasons, and it did not wobble. Every single step moved in the same direction, and because anomalies are abstractions, here is the underlying water temperature rather than the departure from it. The Niño 3.4 region went from 25.97 degrees Celsius to 28.71. That is a rise of 2.74 degrees in absolute terms in the actual temperature of the actual ocean over about a year and a half. So what is El Niño physically? Because it is usually described as if it were a weather pattern, and it is not. It is an ocean event that the atmosphere responds to. Under normal conditions, the trade winds blow steadily from east to west across the tropical Pacific. Those winds drag surface water westward with them, and they do it relentlessly year after year, so that warm surface water physically piles up on the western side of the basin. Near Indonesia and the Philippines, the sea surface actually sits measurably higher than it does off South America, and the warm layer there is enormously deep. Meanwhile, on the eastern side, all that water being dragged away has to be replaced from somewhere, and it is replaced from below by cold water welling up from the deep along the coast of South America and out along the equator. That upwelling is what makes the eastern equatorial Pacific one of the coldest, most nutrient-rich stretches of tropical ocean on Earth, and it is why the fisheries off Peru are what they are. El Niño is what happens when the trade winds weaken and that whole arrangement lets go. The warm water piled up in the west sloshes back east. The cold upwelling in the east shuts down or weakens dramatically, and a vast tongue of unusually warm water spreads across the central and eastern equatorial Pacific, where cold water is supposed to be. For this basin, for the hurricanes we have been talking about, that produces 2 effects at once, and both of them are on the list of 5 ingredients. The first is warmer water across the eastern Pacific hurricane region. Ingredient 1, handed over. The second is a change in the upper-level wind pattern that reduces vertical wind shear over that same region. Ingredient 3, handed over. 2 of the 5 constraints removed simultaneously, across an entire basin, for a season. That is what an El Niño does to the eastern Pacific, and it is the standard, textbook, entirely expected explanation for why this basin gets busy in these years. The reason the shear changes is worth one more sentence because the mechanism is not obvious. The atmosphere over the tropical Pacific runs a great overturning loop called the Walker circulation. Air rising over the warm western pool, flowing east at altitude, sinking over the cool eastern Pacific, and returning westward at the surface as the trade winds. That loop is anchored to the temperature contrast between the 2 sides of the basin. When El Niño erases the contrast, the loop weakens and shifts east, and the upper-level winds that used to shear apart storms in the eastern Pacific relax. That same reorganization is why El Niño is not a Pacific story. Shift the location of the largest area of rising air on the planet, and you shift the position of jet streams downstream of it, which changes storm tracks over North America, rainfall over eastern Africa, monsoon behavior over India, and drought risk over Australia and Indonesia. One patch of ocean, a few degrees warmer than it should be, reaches every continent. It is probably the single most consequential recurring pattern in the climate system, and it is measured by that one running average I read out at the top of this part. Now, the forecast, and I am going to be scrupulous about this because it is the one place in this video where the numbers could easily be oversold. Forecast guidance for the rest of 2026 trends toward what is informally called a super El Niño, defined by a Niño 3.4 anomaly exceeding +2 degrees. Model suites show sea surface temperature anomalies exceeding +2 across the whole ENSO region through the summer season, with anomalies peaking above +4.5 in the eastern regions. One widely reported projection places the peak Niño 3.4 value at around +3.59 somewhere between July and December. Here is the part I want to say clearly and then say again. Those are forecasts. They are model projections. They are not observations. The observed value, the thing that has actually been measured in the actual ocean using actual instruments, is +0.98 for the April through June season of 2026. That is a solid El Niño, and it is warming, and that is what we know. Everything above 2 is a projection about the future, and the future has a well-documented habit of ignoring projections. I am telling you what the guidance says because it is relevant and it is the direction the system is pointed. I am not telling you it will happen, and if anyone shows you a headline treating +3.59 as a fact, they have blurred a line that matters. But even taking only the observed value, the situation is straightforward. The Eastern Pacific is under El Niño conditions that are strengthening, in a year when the ocean's total heat content set a record for the 9th consecutive time, and the basin's peak season has not started. And there is one piece of history hanging over all of this that I have been deliberately not mentioning yet. The strongest hurricane ever measured anywhere in the Western Hemisphere also formed in this basin, in October, during one of the strongest El Niño events on record. We will get to that storm. First, we need to talk about a different one. Part 9. 2 storms, 1 ocean. While all of this was happening, the National Hurricane Center was issuing advisories on a second hurricane. Its name is Fausto, and it is sitting in the Central Pacific several hundred miles east of the Hawaiian Islands. It has been there, being a hurricane, for days, and almost nobody has mentioned it because Genevieve has been the more dramatic object in the room. I want to mention it because it changes the shape of the argument. A single extraordinary storm is easy to dismiss. Oceans are large and variable, and somewhere in a basin that size there is always a patch of water doing something unusual. If Genevieve were the only thing happening, the honest read would be that a favourable pocket lined up in the right place at the right time and produced an outlier. And outliers are what a distribution looks like at the edges. 2 hurricanes, in 2 different basins, running simultaneously off the same ocean, is a harder thing to write off as a pocket. It suggests the condition is broad rather than local, and there is a third data point for texture. In the same tracking feed that logged Genevieve at 140 knots, there is a typhoon in the Western Pacific listed at 85 knots. That is a different basin again, on the other side of the ocean. Now hold that alongside what the Atlantic was doing on the same morning. The National Hurricane Center's Atlantic Tropical Weather Outlook, issued at 8 o'clock in the morning Eastern Time on July 27th, reads in its entirety for the North Atlantic, the Caribbean Sea and the Gulf. Tropical cyclone formation is not expected during the next 7 days. That is the whole product. There is nothing to discuss. A full week of forecast in a basin that is supposed to be spinning up toward its own peak season, and the professional judgment is that nothing will form at all. I want to give that outlook its proper weight, because a 7-day zero is a stronger statement than it appears. These outlooks normally deal in probabilities, a disturbance with a 20% chance of development over 2 days, a wave coming off Africa with 60% over 7. Forecasters hedge, because the tropics reward hedging. A flat declaration that nothing will form over an entire week means the environment is not marginal or uncertain. It is closed. The atmosphere over the tropical Atlantic is doing something so hostile to tropical cyclone development that there is nothing worth assigning a percentage to. Fausto's position deserves a moment too because of where it is. Several hundred miles east of the Hawaiian Islands is a genuinely unusual address for a hurricane. The Central Pacific is a comparatively quiet basin. It produces a handful of storms in a typical year, and many of those are systems that wandered in from the east rather than forming there. The water in that stretch of ocean is normally marginal, and marginal water is where hurricanes go to weaken. A hurricane maintaining itself out there is its own small piece of evidence, sitting alongside the larger one further south. Now, the tempting move here is to treat that as a paradox, a raging Pacific and a dead Atlantic, as though the two were somehow in competition. It is not a paradox. It is one mechanism producing two opposite outcomes, and the mechanism is the thing we spent the last part on. El Niño reduces vertical wind shear across the eastern Pacific. It increases vertical wind shear across the tropical Atlantic. The same reorganization of the Walker circulation that relaxes the upper-level winds over one basin strengthens them over the other. It is one atmospheric adjustment with two signs. So the Atlantic's silence is not evidence of a calm planet. It is evidence of a redistribution. The energy did not go anywhere. The ocean did not become less warm. The atmosphere did not become less loaded. The conditions that permit storms to organize simply moved, and they moved into the basin that just produced a Category 5 in July. I raise this because I think there is a genuine risk of drawing the wrong lesson from a quiet Atlantic. Someone living in Florida or the Carolinas reading a 7-day outlook that says nothing will form could very reasonably conclude that this is a mild year. It might well be a mild year for them. It is not a mild year for the ocean. Those are different claims, and only one of them is about the water. There is a broader version of this error that shows up every year, and it is worth naming so you can spot it. People assess hurricane seasons basin by basin, because that is how forecasts are issued and how news is reported. A quiet Atlantic season gets described as a quiet season, full stop, as though the Atlantic were the planet. It is not. It is one basin among 6, and it is not even the busiest one. The Western Pacific produces considerably more tropical cyclones in a typical year than the Atlantic does, and almost none of them are covered in North American media unless they hit something. So when you hear that a season was mild, ask which basin. The energy in the system did not take a year off. It went somewhere, and the place it went is decided by the pattern, and this year the pattern is pointing at the ocean off Mexico. The ocean is running 2 hurricanes right now and declining to run any in a third basin, and all 3 of those facts are the same fact. Part 10, October 2023. Everything up to this point has been about a storm that will not hurt anyone, over water that nobody lives near, measured by instruments that nobody watches. It has been, in the most literal sense, an academic exercise. Now I want to tell you what happens when it is not. Acapulco sits on the Pacific coast of Mexico in the state of Guerrero, wrapped around a deep natural bay. It is a city of hundreds of thousands of people. It has been a major resort destination for the better part of a century, which means the shoreline is dense with high-rise hotels, and behind the hotels the hillsides are dense with neighborhoods that are not resorts at all. In late October of 2023 there was a storm offshore. Its name was Otis. Otis was, for most of its life, entirely unremarkable. It formed late in a season that was winding down. It was a tropical storm, and then it became a Category 1 hurricane, and the forecast said what forecasts say about a late-season Category 1 approaching a coastline. Here is the specific fact I want you to hold, because everything else in this part hangs on it. Less than a day before landfall, the official forecast called for Otis to peak as a Category 1 hurricane. Consider what that means for a city, operationally, on the ground. A Category 1 forecast is not nothing. It triggers real preparation. People board windows, boats get moved, officials issue advisories, low-lying areas near the water may be cleared, hotels move guests away from the beachfront floors, and everyone expects an unpleasant, noisy, expensive night with some flooding and a lot of downed trees. What a Category 1 forecast does not trigger is a mass evacuation. Nobody empties a city of several 100,000 people for a Category 1. It would be an irrational response to the information available, and no emergency manager anywhere in the world would order it. So Acapulco prepared for a Category 1. Otis went from Category 1 to Category 5 in less than 24 hours. Let me give you the rate, because the rate is the thing. In the 24 hours before landfall, the storm's maximum sustained winds increased by 115 miles an hour. Compare that to what we have been discussing all night. Genevieve did roughly 80 miles an hour in about 30 hours, and I have spent an hour and a half telling you that 80 and 30 is extraordinary. More than double the official rapid intensification threshold, sustained across more than one 24-hour window. Otis did 115 in 24. It was faster than Genevieve, substantially faster, and it did it pointed directly at a city. Otis made landfall at Acapulco on the 25th of October 2023, with sustained winds of 270 kilometers an hour, about 165 miles an hour, and gusts reaching 330 kilometers an hour. The people in those buildings had gone to sleep expecting a Category 1. At least 52 people died. The damage came to an estimated 12 to 16 billion United States dollars, which made Otis the costliest tropical cyclone in Mexico's recorded history. Photographs from the following morning showed high-rise hotels along the bay with their glass facades entirely removed, not broken, removed, floor after floor of rooms open to the air like a cross-section diagram. The hillside neighborhoods behind them fared worse, because they were built of lighter materials and had never been designed for anything approaching that. To put the cost in perspective, Mexico has been hit by considerably more famous storms than Otis. It has been hit by storms with higher wind speeds at their peak. None of them cost this much, and the reason is not that Otis was uniquely powerful. It is that Otis was uniquely unexpected, and it arrived at full strength on a city that had prepared for something 4 categories weaker. The timing compounded it. Late October is the tail end of the Eastern Pacific season. By that point in the year, the basin is winding down, the water is beginning to cool, and the operational and psychological posture of everyone involved has shifted toward the end of the season rather than the middle of it. A late October Category 1 is exactly the kind of storm that closes out a year quietly. And now the cause, which is the reason we are here. The intensification was attributed to record-high sea surface temperatures. As Otis approached the shore, it crossed a patch of water measured at 31 degrees Celsius. 31 degrees, against a maintenance floor of 26.5, several degrees above the average expected for that stretch of coast in late October. Several degrees does not sound like much, and this is precisely where intuition fails people, so let me connect it to the mechanism we built earlier in this video. The rate at which water evaporates off a sea surface does not increase linearly with temperature. It climbs steeply. Warmer water hands moisture to the air above it disproportionately faster, and every gram of that moisture carries latent heat that gets released higher up in the storm's core. So a few degrees of extra sea surface temperature is not a few percent more fuel. It is a substantially larger fuel flow into an engine that was already running, and that is only the surface. What made Otis's patch of water genuinely dangerous is the same thing that made Genevieve's dangerous. The storm crossed it in its final approach and never chilled it. The warmth went down far enough that Otis's own churning could not reach anything cold enough to slow it in the last 24 hours, when slowing down was the only thing that could have saved Acapulco. I want to lay the two storms side by side now, because the comparison is the entire point of this video, and I do not want it to be subtle. Same basin, same ocean, same mechanism, a warm, deep reservoir with low shear over it and an organized core sitting on top. Same behavior, an ordinary hurricane converting into a top-of-scale hurricane in roughly a day. Same speed class, with Otis actually the faster of the two. One difference. Genevieve's patch of hot water was 500 miles from anything. Otis's patch of hot water was directly offshore of a city of several 100,000 people. That is it. That is the whole difference between a video about oceanography and a disaster that killed 52 people and cost more than any storm in Mexican history. Not the storm, not the physics, not the ocean, the longitude. And I want to press on that, because there is a version of this story where the difference is treated as a lesson about Acapulco specifically, about building codes, about coastal development, about a resort city that grew faster than its infrastructure. Those conversations are worth having, and they are not what this is. The difference was not preparedness. Acapulco was as prepared as a Category 1 forecast permits any city to be, which is the correct amount of prepared for the information that existed. If you had given the same city the same forecast for the same storm and moved the hot water 200 miles further out, Otis would have peaked offshore, weakened on approach, and come in as a strong Category 3 that damaged the waterfront and killed almost nobody. Same city, same codes, same response, different water. Conversely, put Genevieve's patch of ocean where Otis's was, and Genevieve becomes the disaster instead. Nothing about the storm would need to change. It is already doing everything Otis did, which means the variable that decided whether 52 people lived or died was not anything that a person, a city, or a government controlled. It was where the heat happened to be. That is an uncomfortable thing to sit with, and I do not have a way to make it more comfortable. Preparedness matters enormously. I have said so on this channel many times, and I will keep saying it. But preparedness operates on the information you are given, and the information depends on a forecast, and the forecast depends on knowing what is in the water. There is one more element of the Otis story that I have been holding, and it is the part that turns this from a tragedy into a warning, because it is the part that will happen again. The intensification outran the warning system, not the buildings. Buildings can be strengthened, and over time they will be. Not the emergency response, which by all accounts did what it could with what it had. The warning, the information, the 12 hours or so between when anyone understood what was actually coming and when it arrived. People in Acapulco went to bed on a Category 1 forecast because that was the best forecast available, produced in good faith, using the best tools that existed. I think about what those 12 hours would actually have been worth, and it is a difficult thing to hold. 12 hours is not much. It is not enough to empty a city of several 100,000 people, and anyone who tells you otherwise has never tried to move a population. But 12 hours is enough for a great many smaller decisions that add up to survival. It is enough to move away from a glass wall. It is enough to get to an interior room, or a lower floor, or a neighbour's more solid house. It is enough to fill containers with water, charge a phone, put documents in a bag, and tell someone where you are. The difference between a Category 1 warning and a Category 5 warning is not primarily about evacuation routes. It is about whether people take the storm seriously enough to change what they do that evening, and the forecast that reached them said Category 1, which is a storm you sleep through with the windows taped. The tools were wrong, and I need to explain exactly how they were wrong, because it is not the story most people assume. Part 11. The forecast that failed. Every computer model got it wrong. Not most of them. Not the majority, with a few dissenting outliers that were ignored. All of them. The forecast failure with Otis occurred within a window of roughly 12 hours, and within that window the entire modelling apparatus, the global models, the regional hurricane models, the statistical intensity guidance, the ensembles, predicted gradual intensification. There was no split in the guidance. There was no minority opinion warning of catastrophe that a forecaster overruled. The models agreed with each other, and they were collectively, uniformly wrong by 4 categories. The moment of realization did not come from a model at all. It came from an airplane. Forecasters began to understand that their guidance had failed only after reconnaissance aircraft flew into the storm on Tuesday evening and took direct measurements. It is worth explaining what that means, because hurricane reconnaissance is one of the more remarkable operations in the sciences, and most people are only vaguely aware it exists. Specially equipped aircraft fly directly into hurricanes, through the eye wall, into the eye, and out the other side, often repeatedly. They measure the wind at flight level directly. They drop instrument packages called dropsondes, which fall on small parachutes while transmitting temperature, humidity, pressure and wind all the way down to the sea surface. And critically, they measure the central pressure by physically being in the middle of the storm. Everything else, every satellite estimate, every intensity guess made from the appearance of clouds from orbit, is inference. The aircraft is ground truth. And on that Tuesday evening the ground truth came back, and it did not match anything the models had said. By then, Acapulco had somewhere in the neighbourhood of 12 hours. So why do the models fail at this specific thing? There are 2 reasons, and both of them are structural rather than incidental, which is why this problem has not simply been solved. The first is scale. Rapid intensification is governed by processes happening inside the storm's core. The arrangement of convective towers around the eye wall, the fine structure of the inflow layer, the way a burst of deep convection near the centre can spin up the circulation. Those processes operate on scales of a few kilometres or less. Weather models divide the atmosphere into a grid, and until recently operational hurricane models used grid spacing too coarse to resolve that structure directly. What cannot be resolved has to be approximated, and approximations of a process that is inherently violent and nonlinear are exactly where a forecast goes wrong by 4 categories. The second reason is the ocean, and it takes us straight back to the centre of this video. To forecast intensification correctly, you need to know not just the sea surface temperature, but the subsurface structure, how deep the warm layer runs, how much heat is actually available. That data is far sparser than atmospheric data. The float network is excellent for computing a global annual figure and much thinner for telling a forecaster what is under a specific storm on a specific afternoon. The result is a lopsided discipline. Track forecasting, where a storm is going, has improved enormously across recent decades. The 5-day track forecast today is roughly as good as the 3-day forecast was a generation ago, which is a genuine scientific triumph and has saved an enormous number of lives. Intensity forecasting has improved far more slowly. and rapid intensification is the widest part of that gap. Which brings us to the research and to the question of whether Otis was a freak event or the leading edge of something. Kieran Bhatia, working at NOAA's Geophysical Fluid Dynamics Laboratory, along with colleagues, published a study in the journal Nature Communications under the title Recent Increases in Tropical Cyclone Intensification Rates. The finding was that Atlantic hurricanes showed highly unusual upward trends in rapid intensification across the period from 1982 to 2009, trends that could only be explained by including human-caused climate change as a contributing cause. Specifically, the proportion of 24-hour intensification rates exceeding 30 knots increased significantly across that period. The window matters, and it is worth understanding why the study starts in 1982 rather than earlier. That is roughly when the satellite record becomes consistent enough to compute intensification rates reliably across an entire basin. Before that, storms in remote parts of the ocean were sampled irregularly or missed entirely, and you cannot detect a trend in intensification rates if half your storms were never measured while they were intensifying. The start date is not cherry-picking. It is the point at which the data becomes good enough to ask the question. The phrase could only be explained by including human-caused climate change is also doing something specific, and it is worth being precise about it, because this is the part that gets distorted in both directions. It does not mean anyone proved a particular hurricane was caused by warming. What it means is that researchers ran the observed trend against simulations of natural variability alone, the internal wobbles of the climate system, the ordinary noise, and the observed trend sat outside what that noise could produce. Add the human-caused warming signal to the model, and the observed trend falls inside the range. That is what attribution looks like. It is a statement about distributions, not about individual events. 30 knots. That is the rapid intensification threshold. The share of storms clearing that bar went up, and the increase could not be reproduced by natural variability alone. Kerry Emanuel of MIT, one of the field's central figures, put the theoretical version of it this way. His own work, he said, shows that rates of intensification increase more rapidly than intensity itself as the climate warms, so that rapidly intensifying storms may be expected to become more common. I want to unpack what that quote says and, just as importantly, what it does not say. It does not say hurricanes will become vastly stronger. The theoretical maximum intensity does rise as the ocean warms, but it rises modestly. This is not a claim that we are heading for 250-mile-an-hour hurricanes. What it says is that the rate of change increases faster than the endpoint does. The storms are not going to be dramatically more powerful. They are going to get powerful dramatically more quickly. That is a subtle distinction, and it is the difference between an inconvenience and a body count. There is more recent work pointing in the same direction. Balaguru and colleagues, publishing in the journal Earth's Future in 2024, documented a global increase in nearshore tropical cyclone intensification, storms strengthening in the final stretch before landfall. I want to be clear about why nearshore is the worst possible category for this trend to appear in. A storm that intensifies rapidly in the open ocean, 1,000 miles from anywhere, is Genevieve. It is interesting. It is harmless. Forecasters watch it, adjust their guidance, and by the time it approaches anything, the estimate has been corrected several times over. A storm that intensifies rapidly in the last 24 hours before landfall is Otis. There is no time to correct the guidance, because the guidance and the landfall arrive together. The intensification eats the warning window directly, and NOAA's Geophysical Fluid Dynamics Laboratory maintains, as its standing assessment, that theory supports rapid intensification events becoming more frequent and more severe as the climate continues to warm. So let me state the danger as precisely as I can, because I think it is almost always framed wrong. The threat is not that hurricanes are becoming unimaginably powerful. Category 5 already existed. Patricia already happened. The ceiling was already high enough to destroy anything we build. The threat is that the interval is shrinking. The interval between the moment a storm looks manageable and the moment it becomes catastrophic. That interval is not a technical detail. That interval is where evacuation happens. It is where people decide whether to leave. It is the only thing standing between a strong storm and a mass casualty event. And that interval is a function of how much heat the ocean has ready to hand. There is a version of this problem that is solvable, and I do not want to leave you with the impression that nobody is working on it. Model resolution has improved substantially since 2023 and continues to. The The grid spacing that failed to resolve Otis's core is not the grid spacing operational forecasters are using now. Machine learning approaches are being applied specifically to the rapid intensification problem because it is exactly the kind of pattern recognition task where they can outperform physics-based guidance. And the observational gap, the sparse picture of what is under a storm rather than around it, is being addressed by expanding subsurface measurement into the places that matter, including instruments dropped directly ahead of storms to profile the water they are about to cross. None of that is finished. All of it is being pushed against, hard, by people who watched what happened at Acapulco and understood exactly what it meant. But every one of those improvements is a race against a moving target, because the thing making rapid intensification more likely is not waiting for the models to catch up. Genevieve did exactly what Otis did. Same ocean, same mechanism, comparable speed. It just did it with nobody downstream, which is the only reason we are having a conversation about oceanography this week instead of counting bodies. Part 12. The ceiling. 215 miles an hour. That is the highest 1-minute sustained wind speed ever reliably recorded in a tropical cyclone anywhere on Earth, and it belongs to Hurricane Patricia in October of 2015 in this basin. Not the Atlantic, not the Western Pacific, which is larger and busier and produces the storms that hold most of the other records. Here, the Eastern Pacific off the coast of Mexico, in the same stretch of ocean we have spent the last 2 hours discussing. Patricia's minimum central pressure was 872 millibars. Set that next to Genevieve's 929, which I described earlier as a deep hole in the atmosphere, and which it genuinely is. Patricia's hole was 57 millibars deeper. To put that gap in context, 57 millibars is more than half the entire distance between an ordinary sea level day and the inside of Genevieve's eye. Patricia went that much further past a storm that is currently at the top of the Saffir-Simpson scale. It made Patricia the most intense tropical cyclone ever recorded in the Western Hemisphere, and the second most intense anywhere in the world by barometric pressure. There is a physical reason storms like Patricia are able to reach numbers like that, and it connects directly to everything we have covered tonight. Patricia was small, extremely small as hurricanes go, a very tight core with an unusually compact eye. Size and intensification speed are related in a way that is not obvious. A large hurricane has an enormous amount of air in circulation, and changing the rotational speed of all that mass takes time and energy. It has inertia in the most literal sense. A small, compact storm has far less mass to accelerate, which means that when the environment hands it favourable conditions, it can convert those conditions into wind speed very quickly. The same energy input produces a much larger change in a smaller system. Compact hurricanes are therefore the ones that produce the most spectacular intensification numbers, and also the ones that weaken most dramatically when conditions turn, which is exactly what happened to Patricia on approach. The tight core that let it reach 215 miles an hour over open water is the same tight core that came apart quickly once it met land interaction. That cuts both ways for anyone hoping it is reassuring. A compact storm can fall apart fast. It can also assemble itself fast, and it does not need a large area of favourable ocean to do it. It only needs a small one in the right place. What saved Mexico from Patricia was a combination of luck and geometry that had nothing to do with anyone's decisions. The storm weakened substantially in the hours before landfall, a very intense, very compact hurricane running into land interaction and a hostile approach, and it came ashore on a sparsely populated stretch of the southwestern coast as a Category 4, which is still an enormous storm. It was also, in terms of where it happened to arrive along several hundred miles of coastline, close to the best possible outcome available. A slightly different track and Patricia would be the deadliest storm in the country's history, rather than a near miss that people outside meteorology have largely forgotten. There is a detail about 2015 that I have been saving. The winter of 2015 into 2016 produced one of the strongest El Niño events in the observational record. So the strongest hurricane ever measured in the Western Hemisphere formed in this basin, in October, during a very strong El Niño. I want to be careful with that sentence, because it would be extremely easy to turn it into a prediction, and it is not one. One case is not a law. Patricia is a single event, and single events do not establish causation no matter how neatly they line up with a theory. There have been other strong El Niño years that did not produce anything like Patricia, and there will be others. What one case does establish is a demonstrated outcome. We are not speculating about whether the pairing of a very strong El Niño with the Eastern Pacific's warmest water can produce a storm at that intensity. We know it can because it did, and we have the pressure reading. There is one other thing Patricia established, and it is the reason forecasters treat this basin with a particular kind of respect. It demonstrated that the Eastern Pacific's theoretical ceiling is not a distant abstraction that storms approach and never reach. Patricia reached it, under the right combination of very warm, very deep water and a favourable atmosphere. A storm in this ocean got all the way to the physical limit of what the environment could support, and the limit turned out to be higher than the record books had previously suggested. That is worth remembering when you hear a Category 5 described as the top of the scale. The scale tops out, the ocean does not, and it is worth holding the base rate alongside it, the same way we did earlier, because the discipline matters. 14 Category 5 hurricanes in this basin since the early 1970s, 3 in 2018, 2 in 2023, 1 in 2024. Genevieve is the 15th. This ocean does this. It is not new, it is not unprecedented, and anyone telling you a Category 5 in the Eastern Pacific is by itself a sign of something is overselling. But Patricia is the ceiling reading. It is the highest number this particular patch of ocean has ever posted, and it posted that number under conditions that resemble, not match, resemble, the conditions now developing. And the quantity that sets that ceiling in the first place, the amount of heat stored in the water available to be converted into wind, is the one that has been setting a record every single year for 9 years running. Part 13. What people are saying and what the data shows. We have 3 things on the table now. A storm that hurt nobody. An ocean carrying more stored energy than at any point in the instrumental record. And a city that was told to expect a Category 1. Before I put those together, I want to deal honestly with the explanations that circulate whenever a storm like this appears, because some of them are going to be in the comments under this video, and they deserve a real answer rather than a dismissal. Start with the biggest one, and start with the fact that it has a specific history attached to this exact scenario. After Hurricane Otis destroyed Acapulco, a theory spread widely online that the storm had been deliberately created or deliberately steered, a directed weather attack, aimed at a specific city by someone. I want to take a moment to explain why that theory is psychologically compelling, because I think mocking it is both unkind and useless. Look at the shape of the event. A storm materialized out of nothing. The official forecast was wrong, not slightly wrong by 4 categories, wrong in a way that has almost no precedent. A city was devastated in a single night, and the explanation offered afterward was, in effect, that the computers did not see it coming. If you're standing in the wreckage of your own neighborhood, the computers did not see it coming, is a deeply unsatisfying sentence. It sounds like an excuse, and the human mind, confronted with a catastrophe and an inadequate explanation, reaches for agency. Something this precise and this destructive feels like it must have been aimed. That is not stupidity. That is a very old and very normal way for people to respond to a disaster. It is also wrong, and the reason it is wrong is energy. A mature hurricane releases energy at a rate that is difficult to convey. Depending on how you account for it, the kinetic energy of the wind field alone, or the total latent heat released by condensation inside the storm, the figure comes out at somewhere between many times and many hundreds of times the entire electrical generating capacity of human civilization, continuously, for days, across a footprint hundreds of miles wide. There is no facility, there is no fleet, there is no device. Nothing humanity has ever built operates within orders of magnitude of that scale, and steering an object that size would require even more energy than creating it, because you would be pushing against the entire mass of the atmosphere it is embedded in. And there is the observational argument, which for Genevieve specifically is airtight. This storm formed and intensified in open ocean, in daylight and darkness, under continuous observation by multiple independent national agencies with different satellites, different aircraft, different buoy networks, and different governments. There is no version of events in which something was done to that water, and nobody noticed. The second theory is the one about ionospheric heating facilities and geoengineering programs, and it fails on 2 independent grounds. The first is altitude. Ionospheric research facilities operate on a layer of the atmosphere that begins roughly 60 kilometers up and extends to several hundred. A hurricane is a lower atmosphere machine. Its engine is the interface between the sea surface and the air immediately above it, and its exhaust tops out around 15 kilometers. Those two systems are not physically coupled in any way that could transfer meaningful energy from one to the other. The second is power, and it is the same argument as before. The energies involved differ by so many orders of magnitude that the comparison stops being meaningful. The third theory is that solar activity triggered it, and this one I am delighted to address, because tonight we have the cleanest possible control condition sitting right in front of us. On the day Hurricane Genevieve reached Category 5, here is what the Sun was doing. The planetary K index, the standard measure of geomagnetic disturbance, reached a maximum of 2 over the preceding 24 hours. 2 on a scale that runs to 9. Solar wind speed was 366 kilometers per second, which is nominal, unremarkable background. The north-south component of the interplanetary magnetic field was positive 1 nanotesla, northward, which is explicitly described in the space weather assessment as not geoeffective, meaning the field orientation was actively unfavorable for coupling energy into Earth's magnetosphere. Auroral hemispheric power was 14 gigawatts north and 14 gigawatts south, against roughly 50 gigawatts for genuinely active conditions. And all 3 NOAA space weather scales, geomagnetic, solar radiation, and radio blackout, read 0, nothing. On the day a Category 5 hurricane formed, space weather was doing absolutely nothing. If solar activity drove hurricane intensification, this is the day it should not have happened. This is the null case. And it happened anyway, over 94-degree water, in a basin under El Niño conditions. The fourth theory deserves the most care, because something genuinely did go wrong, and pretending otherwise would be dishonest. The claim is that they knew, and did not warn Acapulco. Here is my honest answer. The failure was real. The concealment was not. Every computer simulation predicted gradual intensification. Not most of them, all of them. The revision came only after reconnaissance aircraft flew the storm and returned direct measurements. And then, afterward, the National Hurricane Center published its own report on the storm, documenting the forecast bust in detail, in public, under its own name. That is the part that settles it for me. An agency covering up a failure does not write the post-mortem, publish it, and put it on a website where anyone can download it. The existence of the report is the evidence against the theory. What happened at Acapulco was not a secret withheld from people. It was a limitation of the science, described openly by the people whose science it was. The fifth theory is that a Category 6 exists and is being suppressed to keep people calm. This one is easy, and it is based on a simple misunderstanding. The Saphir-Simpson scale is open-ended at the top. Category 5 is defined as 157 miles an hour and above, and there is no upper bound written into it. Nothing is capped, because there is no cap to hide behind. Patricia's 215 miles an hour was reported publicly as a Category 5 with the number attached. The reason there is no Category 6 is that the damage descriptor stops changing. Total destruction is total destruction, not because anyone is hiding a rung. And then there is the sixth claim, which is aimed squarely at the thing this entire video rests on. The ocean data is exaggerated. I want to answer this one properly rather than defensively, because you should not take my word for the central number in a 2-hour video, and I would rather you were skeptical than credulous. The ocean heat content figure came from 55 scientists working across 31 research institutes in 10 separate research teams, based in multiple countries with different governments, different funding structures, and different national interests. The measurement rests on an international network of autonomous floats that no single country controls, cross-checked against satellite altimetry, which measures a completely different physical quantity, sea surface height, and arrives at a consistent answer. It was published in a peer-reviewed journal. It is the 9th consecutive record, and the sea surface temperature record for 2026 was confirmed independently in 2 separate datasets, built by separate institutions with separate processing chains. Coordinated exaggeration requires coordination. What is described above is the opposite of coordination. It is many groups of people with no particular reason to agree, checking each other's work with different instruments and getting the same result. So take every one of those 6 explanations, examine it properly, and notice where they all leave you. They leave you back at the water. I want to say one more thing about why I go through these at length instead of skipping them, because I know some of you find this section frustrating and would rather I got on with the science. The reason is that every one of those theories exists because something real was left unexplained. The Otis forecast failure was real. The gap between what people were told and what arrived was real. The feeling that an institution failed and then explained itself in language nobody could use is real. Theories grow in that gap, and they grow specifically because the gap was never filled with something better. If the answer to Acapulco is, the models were wrong, and here is exactly how, and here is what is being done about it, then people have something solid to hold. If the answer is a shrug, the gap stays open, and something else moves in. I would rather fill the gap. And in this case, the true explanation is more unsettling than any of the invented ones, which does not happen often. Nobody aimed that storm. Nobody had to. Every external cause tested against the evidence drops out. Nothing was manufactured. Nothing was steered. Nothing in space contributed. Nothing was concealed. And nothing is being hidden at the top of the scale. What remains, when all of it is cleared away, is a hurricane that doubled its wind speed in 30 hours because it was sitting on an ocean that had the fuel to let it. Part 14. The Warning Shot. So let me answer the question in the title, directly, with no more hedging. A Category 5 formed 500 miles off the coast, and that is not the worst part. The worst part is the water. Here is the case, compressed. A storm went from 80 miles an hour to 160 miles an hour in about 30 hours, more than double the official threshold for rapid intensification, sustained across more than one full day. It did that over water reported between 86 and 94 degrees Fahrenheit against a survival floor of 80. It did not choke itself on its own cold wake, which means the warmth ran deep, which means it was drawing on stored heat rather than a surface skin. And it did this in a year when the total heat content of the top 2,000 meters of the world ocean set a record for the 9th consecutive time, during an El Niño that is still strengthening, in a basin whose peak season has not started. And the published research, stated carefully, says this: rapid intensification rates have been increasing. That increase has an attributable human-caused component, and the fastest growing subcategory of it is the nearshore case. Now I want to say the danger one more time, in the plainest words I have, because it is counterintuitive and almost everybody gets it backwards. The problem is not stronger hurricanes. The problem is shorter warnings. Think about the asymmetry. A Category 5 that is forecast 3 days out is a survivable event. It is expensive and it is traumatic and it destroys property, but people leave. Highways run one direction. Shelters fill. The vast majority of the population is somewhere else when the eyewall arrives, and the death toll ends up remarkably low relative to the destruction, because the warning did its job. A Category 1 forecast that becomes a Category 5 overnight is not survivable in the same way, because nobody left. There was no reason to leave. The information said stay, tape the windows and go to bed. 52 people, one wrong forecast, 12 hours. That is what the shrinking interval costs, and it is the only number in this video that is made of people. And notice that nothing in that sentence is about the storm being too strong. Acapulco could have survived a Category 5 it saw coming. Cities do, routinely, all over the world. What it could not survive was a Category 5 it had been told was a Category 1, because the strength of a hurricane and the strength of a warning are two different things, and only one of them can be improved by building better. We have spent decades getting very good at the first problem. Structures are stronger, codes are better. Emergency management is more sophisticated than it has ever been. Every one of those improvements assumes a warning arrives in time to activate them. The trend we have been discussing all night attacks the assumption rather than the response. It does not make the storm harder to survive. It makes the warning harder to give. Which brings me back to Genevieve, one last time, and to why I have spent 2 hours on a storm that will not so much as knock a tile off a roof. Genevieve ran the identical process. Same ocean, same mechanism, same class of speed, and by every measurement we can take it did what Otis did. The only difference is that it did it in a place where it could not reach anyone, which makes it the clearest possible demonstration of what this ocean is now able to build, and how fast without a single person having to pay for the demonstration. It is a warning shot, fired over open water, where we can watch it, measure it, and understand exactly what we are looking at no cost. Warning shots only work if somebody reads them though, and this is the part that worries me most. A storm that harms nobody generates one news cycle and then vanishes. It will trend today, it will be gone by Thursday. There is no follow-up coverage of a hurricane that did not hit anything, because there is nothing to follow up on. No damage assessments, no recovery, no anniversary. The entire informational life of Hurricane Genevieve is about 48 hours long. Meanwhile, the thing it measured stays exactly where it is. That asymmetry is the whole problem in miniature. The events that get attention are the ones with wreckage in them, which means we systematically pay attention to the ocean only after it has already spent its energy on someone. A clean reading, taken in advance, at no human cost, gets treated as a non-story precisely because nobody was hurt. I would argue the opposite. This is the most useful hurricane of the season, and it is useful because of what it did not do. And here is the inversion I flagged at the beginning of this, which I think is the real shape of the whole story. On this channel we usually tell you that the quiet reading is the warning, that the silence is the thing to watch. Tonight it is the other way around, and it is stranger for it. The loud event, the Category 5, the 160-mile-an-hour winds, the number at the top of the scale that made every headline today, is the harmless one. It will be gone in a week. Nobody will remember its name by October. The quiet number underneath it is the warning. 23 zettajoules, published once a year, in a specialist journal, in a unit almost nobody recognizes, describing something happening a kilometre under a surface nobody can see, generating essentially no coverage anywhere. That is the reading that matters, and it is the reading that does not go back down. Let me also be precise about what I am not saying, because I think you are owed that. I am not saying this hurricane was caused by climate change. Individual storms are not attributable that way, and anyone who tells you otherwise is going further than the science does. I am not saying a Category 5 is about to hit anyone. Genevieve is going to die at sea, as forecast, and there is no landfall threat in this story at all. What I am saying is narrower and I think harder to dismiss. The conditions that permit a storm to transform in 30 hours are becoming more common. That is documented rather than speculated. And the specific consequence of those conditions becoming more common is not that storms get bigger. It is that the gap between this is manageable and this is catastrophic keeps narrowing. And that gap is where every warning system, every evacuation order and every decision a family makes about whether to stay in their house actually lives. The ocean has been taking this energy in quietly for decades. It does not announce it. There is no footage of it. It simply accepts what arrives and holds on to it, and the number goes up, and almost nobody looks. There is something almost patient about it, and I mean that in the least comforting way I can. The atmosphere is dramatic. It produces heat waves and cold snaps and record days and then gives them back, and the whole system swings around and people argue about what any individual swing means. The ocean does not swing. It accumulates. It has been accumulating for as long as the imbalance has existed, and it will keep accumulating for as long as the imbalance persists, and then it will keep holding what it has accumulated for centuries after that, because that is the timescale on which deep water circulates. Everything we have talked about tonight, the 30 hours, the pressure reading, the swell arriving in Baja under a clear sky, the 12 hours Acapulco did not get, is the surface expression of something that has been going on underneath, silently, the entire time. Genevieve is what it looks like when a very small fraction of that stored energy gets spent in one place over a day and a half, and the basin's most active period has not started yet. Genevieve reached the top of the scale in the last week of July. The Eastern Pacific's peak runs from late August into September, over water that will have had another full month of summer to absorb heat, under an El Niño that forecast guidance says is still strengthening. So here is the thing I will be watching, and the reason I will be back. Not whether another Category 5 forms in this basin this season. I think that is likely, and it would not be remarkable if it did. The question is where the next one starts, and whether it starts close enough to a coastline that the 30 hours actually matter.